Okay. So, all right, welcome back to Lecture 2 of Computational Geometry. And today I'm going to finish talking about projective geometry. And we'll probably get a little bit into oriented projective geometry and convex polytopes, or begin the discussion of that stuff. But the first thing I want to say is maybe go back a little bit, sort of before, projective geometry, and talk about how you usually see problems presented in a geometric setting, which is through affine geometry. So typically, when you get some problem, it's usually not described in terms of, projective lines and, some homogeneous coordinate system. They're usually described in terms of points and lines and planes in, 3 or 2 dimensions. And so it can be useful to sort of introduce and discuss this kind of simpler model of geometry, which doesn't have, these extra coordinates sitting around in it, for the purposes of describing problems, even though it's not a particularly useful formalism for doing any computations. But in order to say how we can convert from that into the projective one, we still need to say what it is and how it all works. So what I'm going to start with today is to quickly introduce the concept of an affine plane, or an affine coordinate system. So an affine space in n dimensions, which we're going to write as this sort of script an, which is n-dimensional affine space, is basically a real vector space, but without any prescribed origin. So one way to think about this is that it's basically Rn mod translations. And I'll explain what this means now, right? So in affine space, right, so this is kind of the, quotation marks is what we'll say what this is, right? So in an affine space, we have basically 2 different kinds of fundamental structures. We have points and we have vectors. So we have, a point, which we'll usually draw as a dot. So you have 2 objects, points and vectors. So you can draw a point like this, another point here, Q, and then a vector can represent some relative length between 2 points. So this would be Q minus P, right? So between these 2 different types of objects, we have 3 basic operations that we can perform, using just sort of regular arithmetic. So we can, so we have 3 operations. So you can take 2 vectors and add them together, just as you would in a normal vector space. So we have like plus, which takes a vector and another vector, and it spits out a vector. We can also do a plus with a point, right? So we can add a vector to a point. So we take a vector and a point, and it spits out another point. So this would be sort of the act of taking a point and then translating it along some vector and creating a new point. And we can subtract 2 points. All right, which will spit out a vector. All right. Now, one thing that's notably missing from this list is it's not possible to take 2 points and add them together. And that's because, unlike in a vector space, we don't have any well-defined heading or direction for a pair of points. So the way that we would basically parameterize an affine space is that usually you can pick an arbitrary origin, and then you can represent each point as an offset from that origin point using this sort of idea here, right, where you can just take a point, which would be your origin, and then add some vector, which is your coordinate describing that point, and you get the point which is represented by that vector offset. But if we were to try to add the 2 points together, right, so imagine, again here, I'm going to put an origin here. We'll call this O. And I take my points P and Q. Maybe kind of put O a little bit too far out. Let me do this here. right? So say I put my origin here. I take P and Q and represent them by two vectors. If I add them together, using this origin, this would give me 1P plus Q. But in an affine space, I'm going to require that all of my operations should be invariant under wherever I put my origin. So if I put it here, right, and I take 2 points, I add them together, well, I'll get a very different sum, right? This would be my P plus Q. So in this sense, notably, point plus point is not defined. OK, so that's the basic set of operations in affine geometry. And one of the main things that we can do with points in affine geometries is we can take affine combinations of them, which does turn out to be well defined under these operations. So to describe an affine combination, I'm going to introduce a little bit of notation here, which is this concept of an affine hull of a set. So given S contained in affine space, the affine hull, right, this is how it's written, of S, is equal to the sum of all, or it's the set of all affine combinations of S. And so an affine combination is going to be a weighted sum of the elements in S, right? So Wi Si, where the sum of all these, right? The sum of all these Wi's, I'll just write it as sum of Wi, has to be equal to 1. So for example, suppose S was just a set consisting of 2 points. So say I have, this is P0, this is P1. Then I can take any point, here, right? We'll call this guy, say, W0 P1 plus W1, W0 P0 plus W1 P1. And if I extend this out, I can generate the whole line, right? So the reason that this is well defined is that these W's have to sum up to 1. And so what I can do is I can arbitrarily pick any point in S, assuming that it's not empty, to be an origin for S. And then the rest of the points can be represented as vectors. And then taking weighted linear combinations of vectors is well defined. So for example, if I take P0 to be the origin, then by fixing W0, right, I can basically solve for it in terms of all of the other components. And then I will get that W0 is going to be equal to 1 minus W1. And so I'll have 1 minus W1 P0 plus W1 P1 is equal to that. And that's the same thing as saying, I'm basically taking P0 plus W1 times P1 minus P0. All right, so this is basically like an offset, like it's a vector quantity, right? And this is a point. So this is sort of the illustration why this is a well-defined operation. But you can also think of this as, in some sense, being the same analogy of taking a join of two subspaces. So when you take some collection of points and you compute their affine hull, it's like taking the join of all of those points and turning them into a common space. So, OK, sets which can be written as the affine hull of some set. Yeah?
So are you saying that the line that's defined by P on P1 is the affine hull?
Yeah, exactly. So this line here, L is just the affine hull of the set consisting of P0 and P1. Right? So that's how it's defined. And so lines and points and planes, and more generally like hyperplanes, are examples of these affine sets, right, which are called flats. Right? So this is the concept that we'll come to next. So a flat, right, Or I should probably write it like this. We'll say a set S is a flat if S is closed under its own affine hull. So if I take a set and I compute its affine hull, then it's called a flat. All right? And so flats are basically like lines, planes, and so on. And to each flat, we could find some smallest set of points which would generate this flat. All right? So we could think of this as like being a basis. So right. So we'll say for any flat, and I'm just going to state this without proof, right? Because I don't want to get too hung up on it right now. But suffice to say, this is really easy if we sort of move to a projective point of view, right? It's essentially the same thing as the proof that every vector space has a basis. So for any flat, there exists a finite set S. So for any flat F, there exists a finite set S such that F is the affine hull of S, and it's not equal to the affine hull of S minus any one point in SI for all SI and S. Right? So this basically means that it's minimal. So if I take even 1 point out of this set S, then the flat will basically look like something else, right? So if I have this like line and it's written as the affine hull of these 2 points, if I pull out P1, then I'm left with an affine hull of just a single point. So it's going to be just a dot, and it won't be a line anymore. So why is this important? So this allows us to define the rank of F flat, right? So the rank then the rank of a flat F is going to be the cardinality of S. Right? So it's the number of elements in the set. So this you can think of as basically the dimension of the flat. In fact, if we think in terms of a dimension, as a point being 0 dimension, a line being 1 dimension, this is just the dimension of the flat minus 1. It turns out that really, if we had been thinking about dimensions properly, we really should have started counting dimensions at 1 instead of 0 for points, right? But this notation just turns out to be a little more convenient because we'll also like to consider things like an empty flat. And if we're going to work with dimensions, we would like to give this thing maybe a natural number. But in sort of the dimensional counting scheme, it'll turn out that maybe the empty set will have to get a dimension of 0, right? Whereas if we work with ranks, we can just give it the number 0 for empty, 1 for a point, and so on. So really, the concept of a rank of a flat is we're just counting the smallest number of points you need in order to generate that whole flat. So, OK. So that's flats and affine geometry in a nutshell. So, right. So what are some things that we can do with flats? So we can calculate meets and joins, just like we did with subspaces. Right? So it's the same kind of story again. All right. And the reason that this basically works is that flats, like subspaces, form a lattice under containment, and we can form least upper and greatest lower bounds, right? And so we can also define a meet and a join in exactly the same way. So right, so here's sort of the idea. So if you take a flat S and T, then there is a meet, which they both contain. And then there is a join, which contains both of them. So we'll write it this way. So the meet of two flats, S and T, is equal to largest common flat, which is actually just the intersection of S and T. Right? Similarly, we have a join, right, between two flats, which is just the smallest flat containing both. And this is the affine hull of their union. All right. So those are the two basic operations. So we can think of join as just gluing two flats together, building another one, and the meet as intersecting them. Now, it's a little bit weird because these are not quite as well behaved in affine space as they are in subspaces. So for example, if you have two parallel lines, it's not true that they actually will intersect in a flat of some dimension lower. And so this causes this meet and join operation for flats to fail to be distributive. So it forms a lattice, but it's not a distributive lattice. You can't split them up, and the algebra becomes quite a bit nastier. Another kind of problem with this sort of affine model is that when we start looking at transformations of the affine plane or different symmetries of it, it becomes pretty cumbersome to work with. And the last kind of issue is that there's also some sort of intuition that there ought to be some kind of duality here going on between meet and join and these other structures, but it's not really represented in there. And it also just turns out to be really annoying to actually calculate anything in affine coordinates. And so this is what sort of motivates moving to projective geometry. All right, so now kind of get to that and go through the details. Right. So that was affine geometry in a nutshell. And so projective geometry is basically a superset of affine geometry. It's sort of a more general coordinate system. And I will explain now how it works. So now we're going to define n-dimensional projective space. So this is n-dimensional projective space. All right. Okay, and the sort of mental picture, may be helpful or maybe not, is that this is an n+1 dimensional real space mod scaling. All right. So what does that mean? Well, okay. So here's the basic idea. So if we have two vectors and we want to think of the points that they generate in the projective plane, then we're going to consider them to be equivalent if they can be rescaled by some arbitrary real number to the same value, right? So that is, we're going to have this concept of projective equivalence of two vectors. So if we have two vectors v and u in Rn+1, right? So they have an extra dimension into them. We'll say that they're projectively equivalent to one another if and only if there exists some scaling parameter lambda not equal to 0 in Rn and just R, right? Such that v is equal to lambda times u. So that is, if I can basically find some parameter lambda which rescales u so that it's the same as v, then they're the same vector for projective purposes. And here's kind of the picture of how this looks in 2D, right? So for the 2D projective plane, it's actually embedded in a 3D real coordinate system. So we'll imagine that we have this axis x, y, and then we'll have this third component here, which is usually written as w. Then our projective plane is this plane here. So we'll say that this thing is basically P2, and then this vector space here is R3, right? So if we take a point here, call this guy P, and we look at some vector through the origin, this is where P would cross this plane, right? So there are different models for this, right? And there are different ways that we can visualize it. But this is, probably the more common picture that you'll see, right? So in abstract projective geometry, usually this plane here is not prescribed, right? So it's usually not set, to any particular level. But they're like to any particular plane. It just has to not pass through the origin. So you can take wherever you would like, and you can put it there, and then that will form the plane, right? But once you do pick this plane, right, you'll notice that there are these vectors which happen to intersect the plane, and then there are these other vectors which happen to be parallel to it. So for example, if I take a vector which has w component 0, right, like something like this, right, this vector will never intersect this plane. And so you have these extra points sitting around. And these extra points in projective geometry are known as the points at infinity, right? So there's actually a whole line of them, right? So if you imagine, going all the way out here around your whole coordinate system, there's this extra collection of points at infinity. And the reason these things behave in some sense as these points at infinity, right, is that if you think in terms of, perspective artwork, right, mapping a point to one of these points at infinity or like a vanishing point causes, these lines to become stretched and skewed, right? So this gets, used very frequently in graphics and image processing, where you want to model like image projections of 3D scenes onto, 2D surfaces, right? But they also turn out to be useful because if we wanted to consider the meet or join of two flats, if they happen to be parallel, then they might not intersect in this projective plane up here, but they will actually meet at some point at infinity. And this allows this lattice of flats to become much more well-behaved algebraically. So that's sort of the one picture of it. Now, there are other pictures that we can draw of projective geometry, which may be more mathematically illuminating. So this is sort of the flat model, right? So this is kind of a flat picture. There's another point of view, though, which is we can imagine that we start again with a 3D coordinate system. And then what we're going to do is draw a big sphere. All right, and then what we'll do is whenever we pick a point in projective space, it will correspond to some point on the sphere. But because it's also identified along this whole line, it has an antipodal point on this sphere, right, which is basically glued together. So this is kind of the other mental picture of projective geometry, right, which is that it's basically Sn with antipodal points identified. So what this means is that you can think of the surface of the sphere as being projective geometry, but at any given time you can just teleport to the opposite side of the sphere for free, right? So we're going to think of these two opposite points on the sphere as just being glued together, right? Because really what we're just doing is we're just moving around the vectors in this coordinate system, but we don't care about their lengths, right, as long as they're not 0, right? So these two pictures allow us to say a little bit about what the topology of projective space looks like. So if we look here, in this kind of point of view, we can see that projective space looks basically like affine space, except you have these extra points at infinity that you glued around the boundary of all of affine space in order to make it into a compact space. So now you can actually like wrap around or move in a full loop. And what do these points at infinity look like? Well, they look like a projective line that's one-dimensional lower, right? And then that 1D projective line is again going to look like a 1D affine line plus an extra point at infinity that you glued it together with, and so on. So this means that projective space really is the same thing as n-dimensional affine space together with projective space of one dimension lower, which means that it's basically an glued together with an minus 1, glued together with an minus 2, and so on until you get down to just the single point, right? So that's sort of the topological perspective of what projective geometry is, right? Okay, so, all right, that's maybe a little abstract. So let's go to something a little more computational here. All right, so I'm now going to explain how we represent points and flats in projective coordinates. All right, so if you recall from last time, right, I said a little bit about projective geometry, and that basically projective flats are just linear subspaces. There's really nothing else to it. And again, with linear subspaces, we could represent them in one of two ways. We could think of them as being generated by the column space of a matrix or by its null space. Right? So those are the two things, or as the image of a linear function, or as the kernel of some linear map. And so I'm going to introduce two pieces of notation, which are basically adapted from Stolfi's notes, right? So you can look at those online if you want to see that, for describing these two different ways to represent projective flats. So here's the first way. We're going to call this primal representation. You know, or you could also think of this if you do tensor mechanics, it would be like a contravariant vector. You know, so it's like it transforms in a particular way, right? We'll come to this in a moment, right? So here's the sort of notation. So the idea is that we're going to take a series of vectors, P0, P1, and so on, Pn, right? And then this will correspond to the projective flat, which is just formed by all weighted combinations. You know, P0 plus W1, P1, W2, P2. I mean, you get the idea, right? So this is basically this. So we'll basically say each of these PIs, Rn plus 1, is a vector or a point, or however we choose to write it. Okay? So the other kind of interpretation of this is that, you know, as a matrix, write this at capital P, right? P is equal to the image of this matrix that just has P as its column. So we'll have basically P0, P1 to Pn, right? So the rank of this flat is basically going to be the number of points, right? Or it's basically the dimension of the vector space that represents it. All right, so the rank of P, in this case, is going to be, probably should have used a different index here, right? We call this guy K. Yeah. Actually, I want to call it K minus 1, right? Because there's actually going to be K points since I started at 0. So the rank of P will be equal to K, right? So that's the first way to represent a flat, right? So there's a second way, right? There's always two ways, which we'll think of as sort of the dual representation, or as like a kernel. And again, we're going to start with, you know, some collection of vectors vi in Rn plus 1. And then instead of using these angle brackets for writing it, we're going to use, or instead of using square brackets, we're going to use angle brackets to write this out, right? So we'll call this guy, say S, which is going to be equal to V0, V1, and so on, all the way up to Vk minus 1. And this is the collection of all points P equal to x0 to xn, right? Yeah, such that v0, 0, x0 plus v0, 1, x1. In other words, like I take the dot product of each of these v's, right? It's equal to 0 plus plus v1, 0, x0, v1, 1, x1, to vk minus 1, 0, x1, 1, x1. All right. So that's kind of the idea, right? So you can think of these guys as basically generating the rows of a matrix, right? So so in matrix form, I'm going to say S is going to be equal to the null space, or the kernel of V0 transpose V1 transpose Vk minus 1 transpose. And then the rank of S is actually going to be n minus k minus 1. I believe that's correct. Yeah. And the reason is that we should think of, instead of, where each of these guys generates like a new point, right? Each of these things, starts from the whole space, and then we're kind of collapsing it by intersecting it with a hyperplane. So this is sort of the, you can think of this as basically like, affine hull of points. And then in this form, we can think of this as basically intersection of hyperplanes, which is in some sense, what a linear system really is, right? Linear systems are just intersections of hyperplanes. So these are the two ways that we have to represent flats in projective geometry. All right, and we'll often, work between both of them or convert between one or the other and pass between them, right? So it's good to just keep them in mind. And some operations are way easier in this form, and some operations are way easier in this form. And most of the algorithms that we're going to look at in computational geometry, at the end of the day, boil down to either, converting from one representation or the other, or, answering some query, right? And, maybe the query will turn out to be really fast in this form, or maybe really fast in this form, and so on, right? So that's sort of the high-level idea, right, is that we're usually going to be just kind of working between these two things, right? So, okay. Yeah, so now let's come back to meet and join in projective geometry. So these are, again, pretty well-defined operations, and it's relatively easy to calculate them for primal and dual representations, respectively. So, yeah, so I'll say something about the meet, right? So if I take two primal points here, right, I'll have one that says like P0, P1, pk minus 1, and I want to compute the meet of that with q0, q1, ql. Well, in this form, it's just the same as concatenating all of the points in these two lists, right? So this, we'll just say join here is easy, right? It's going to be P0, Q0, and so on. So I just concatenate them, right? Similarly, if I want to calculate the meet of these guys, right, in this form, using angle brackets, then it's also the same thing, right? I basically just concatenate them together. Because all it is I'm just intersecting more planes, right? So I just, like stack the rows on top of each other, and then that's it. All right, so no big deal. So those are the way that you do it. Now, the place where it becomes difficult is if you want to calculate a meet of 2 point sets in the primal version, then you have to do a little bit of work. Or if you want to calculate a join in this dual version, then that becomes a little bit harder, and you have to solve some stuff, right? I mean, usually it involves solving a linear equation to do that. All right, so that's basically how that goes. All right. So, okay, so this is all maybe clear. We have these two representations, right? All right, so we have like, sort of this primal version, which is, represented by just generating, linear combinations, and the dual version, which is represented by intersecting. All right. So now I'm going to talk about duality, right? Which we already saw the basis of last time, right? And if you recall, the way that works is it's basically the same thing as taking a transpose of one of the matrices. Or in this case, it would be the same thing as replacing these square brackets with angle brackets, or angle brackets with square brackets. That's all that's really going on. Or if you think in a vector, kind of context, if you have like a vector, it's the same thing as converting it into its normal plane, right, or the orthogonal plane to it. Right? So this is kind of the picture. So to do this, I'm going to basically start filling up a table here. I need to erase some of these things. Hopefully everyone has all this, or if not, you can try to read it from the video capture, which I think will be good. And if that doesn't work, then I'll probably post some notes. Right, so here's sort of our grand table of duality, right? Right, so this is here's the rule, right? You basically take, anything that looks like this, and then if you put a little star next to it at the top, by convention, we're going to say that this is just equal to replacing all of the square brackets. Oops, make it P with angle brackets. And if we have any angle brackets, and we put a star next to it, and we're going to turn it into square brackets. That's just the high-level idea of what's going on. It's a very simple transformation. We're just flipping like a little symbol inside there. So we can imagine now what this actually implies geometrically. So there's a couple of things, I guess I should say, right? So one is that if we apply the dual operation twice, right? So if we take any flat, right? So for any flat or expression involving flats, right? The dual of it twice is idempotent, right? So or it's an involution. So we'll just say like duality is an involution. And then we have this kind of mental picture for what's going on, right? So if you have, in the sort of, W homogeneous model, right, for projective geometry, if I have a plane like this, I have a point like that, all right? So this guy, there's this 1D subspace, which is generated by the vector through P. Then the dual to P is this orthogonal or subspace, right? So this is basically P star, and it will intersect this projective space somewhere out here in a line, right? I should probably have drawn it a little bit differently, but you can imagine that basically if P is a vector, then this space here is the parallel part of P, and then this would be the perpendicular part, or the orthogonal complement. And so this point here would be P, and this line here would be P star. All right, so that's basically what the dual means in a sort of geometric sense. So I'll give you a couple more examples of, like concretely what duality does, or how it switches things. Right? And so because it's a sort of symmetry, I only need to really fill in like each entry once. So you can also imagine that if you take the dual of the right-hand side of this table, that'll give you the left-hand side. So here's kind of the concept. So I'm going to have two columns here. I'm going to have S and S star. So if I feed it a point, and I take the dual of that point, then I'm going to get an n minus 1 dimensional hyperplane. And more generally, if I feed it in a rank n flat, a rank k flat, I guess, I'm going to get a rank, should be n minus k. Yeah, rank n minus k flat. I believe that's correct, right? So if I feed in a point, get n minus k plus n minus k plus 1 flat. Yeah. All right, so that's the idea. So you can imagine in 2D, right, if I give it a point, then duality is going to spit out a line somewhere, right? If in 3D, if I feed in a point, I'll get a plane out on the other side, or if I feed it a line, I'll get another line. And then in 4D, the pattern basically continues. So you just are reflecting in the dimensions, essentially. Similarly, if I take the meet or the join of two flats, then the dual of this is going to be the meet of their duals. Right? So this is another basic property, right? So if I apply it to join and meet, I'll get that. I mean, obviously, if I feed in something written with square brackets, I'm going to get something, the same thing written with angle brackets. If I take, now here's a thing that's a little bit funny. So if I take the origin, right? Now this is a thing that's a little bit funny about projective geometry. So in affine geometry, there is no well-defined origin. But in projective geometry, it turns out that with duality, you do have a well-defined origin, assuming that you fix some plane at infinity. Because the dual of the origin will be the hyperplane at infinity. And more generally, any flat through the origin becomes a flat at infinity. So in this sense, you can think of duality as like sending the point at the origin to the farthest away point at infinity and all the points at infinity back to the origin. OK. So that's maybe some geometric intuition about projective geometry. Hopefully no one's confused. Yeah.
So with your example there of doing the your primality and taking duality of it, with
yeah.
the P and the P prime with the and the P prime turns out to be your intersection of the planes. How does that go back from? Can you just explain how that goes back from? Like if you're taking the inversion of the evolution of the duality.
For which thing or what?
Picture there.
Oh, for this picture. Yeah. So I was just saying that if I take P, right? Then the dual of P, right, is basically the set of all of these, so if I think of it in the linear algebra sense, because what's actually going on is it's really just, linear algebra, right? It's just a geometric interpretation of the linear algebra picture. So really this P is actually this line through the origin, right? It's this line which is generated by a vector, pointing in the P direction. So the dual of this line, right, is the set of all of the vectors which are perpendicular to it. And that's this plane here, which is P perp, right? So it's like this little P perp down here. So P is formed by taking the line and intersecting it with this plane. And then P star, the dual of P, is formed by taking P perp and intersecting it with this plane. Now to go backwards, right, if I take this line here, this line is actually generated by this whole plane, right? And then the set of all vectors which are perpendicular to this plane is actually the line. So if I take that line again and intersect that back with the plane, I get P. So you can see, if you just if you take the dual of the dual, you get back to where you started, right? That's what that basically illustrates. So hopefully It's not too confusing. Not. Maybe we're okay. All good. Good. Okay. All right. Great. So, all right. So that's duality. We'll come back to this repeatedly, right? But we're going to leave this at that. We're going to leave this for now, right? If it's not all totally clear, don't worry about it. We're just going to keep going through it, and it'll eventually start to turn into something, more simple, over time, right? It'll become less abstract as it becomes more computational. So, all right, but what I next want to talk about are transformations in projective space and affine space, because one of the key differences between projective geometry and affine geometry are the sets of allowable symmetries which they have, or the allowable transformations in the plane. So, yeah. So, right. Yeah. So transformations turn out to be pretty important because in some sense they're actually one way that you can try to classify or define what a geometry is, right? So the difference in some sense between Euclidean geometry and affine geometry and projective geometry is all in the types of allowable transformations in the geometry. So it's when you would consider two different figures to be equal. So one perspective on what a geometry is all really about is it's denoting, or it's basically about classifying figures and diagrams in the geometry. And the way that you can classify a figure is up to symmetry or some type of transformation. And so projective geometry is interesting in that it has a larger allowable set of transformations than affine geometry. And affine geometry has more allowable transformations than, say, Euclidean geometry, right? And there are other geometries which allow for, even more transformations than this. But let me say now a few words about what a transformation is. So, and how we would actually encode them. So in affine geometry, it turns out to be a little bit more ad hoc and kind of messy to write a transformation. And so I won't go into the details for how it would work in affine coordinates, but you can figure it out yourself, right? It's not a big deal. But in projective geometry, transformations turn out to be very nice because they're just matrices. So every sort of translation or rotation or motion in your coordinate system is just some matrix multiplication or a matrix operation. Right. So we'll start out with translations, right? So here's kind of the simplest sort of transformation that you see in either coordinate system. So translations. So here's the idea. So in affine geometry, right, a translation, we'll call it T sub v of a point P, is just P plus a vector, right? So we'll just think of it as translating by a vector, all right? Whereas in projective geometry, we can imagine this as being represented by a matrix. And I'll do this in 3 dimensions now. So we'll imagine that we have a 3D projective space, which is actually going to be represented by a 4D matrix, right? So this would be represented by a matrix V1, V2, right? So to illustrate why this works, right? Imagine I take M and I multiply, some point Px, Py, Pz, right? 1 by this value. Well, then what I'll get is I'll basically have, 1 times Px, right? So it's going to be Px plus V0 times the W component, which here is just going to be 1. So it'll be plus V0, Py plus V1, Pz plus V2, and so on, and then just 1 at the bottom, right? Now you could say, well, maybe this depends on your choice of 1, right? But it wouldn't matter, because if I change this to be some other value, then it would be the same thing as rescaling all of these other guys by the same amount. And I could just divide it off again, right, at the end over here. So without loss of generality, I can just pick the W component equal to 1. So a translation matrix will look like that, right? So now this is basically how you would translate a point, or you apply some matrix transformation to it. And this notation works fine for points written in this primal sense, using the square brackets. But if I write something using the angle brackets, the situation is a little bit different, right? And I'll now explain why, right? So this is basically the projective form, right? So here's sort of the moral, right, that I want to explain, right? So it's basically transformations as matrices. Projective space. So here's the basic idea. So if I have, some matrix M, and I'm going to apply it to a set S, then this better be equal to just M times little s, such that little s is contained in big S, right? So this is how it should be defined, right? That's what we ought to expect. So if I take big M and I apply it to something here, right, using the square brackets, right? Well, this is just the linear combination of all of the elements, in PS, right? So this is just M times, W0, P0 plus, et cetera, Wn, Pn, which is basically just, MP0, MP1, Mpn. So that's easy, right? So this is sort of like the primal case. So what happens to duals? Does anyone want to take a guess? Right, this is a little bit tricky, right? Or does everyone kind of follow this idea, understand what I'm doing with this? Any questions or comments? Ideas? No? Okay. All right, does everyone understand this idea of turning a transformation into a matrix? Right, we're going to just multiply all of the vectors by the matrix, and then we're going to generate new vectors. That's good, right? So, all right, we're all on the same page there. And then in this primal sense, this is easy. I mean, because what I would like to do is I would like to apply a transformation to a flat, right, or something which is generated by some collection of points. So in this case, what I'm going to do is I'm just going to take my matrix M, and I'm going to multiply it by each of the elements here. And this works just because of linearity, right? So it doesn't matter if I multiply with a scalar or multiply with a matrix. Those two things are commutative, right? I can multiply with the matrix, or I can multiply with the scalar, or I can multiply with the scalar, then multiply with the matrix. Fine. But the situation for duals is not quite so simple. And I will show you what it involves. It's not so bad, though. Right? We'll just do it right now. Right? And this is also the basis for this concept of covariant and contravariant vectors, right? Which you maybe have seen in physics, I don't know, or in some other subject, right? I mean, it shows up in a bunch of different places, right? But we kind of run into it right away here, right? So I'll just explain what it does and what the difference is. So if I apply some matrix M to one of these sort of dual representations, well, this is the same thing as applying M to this set of all of these, x's, right? Such that, Q0 transpose x equals 0, Q1 transpose x equals 0, etc. Right? So now, well, what happens, right? Well, I can pull the M into the x on this side of the equation, right? So I'll do that right now. Right? I don't want to save some blackboard space. So just pull the M right in, all right? But I really want to get the M over to the Q's, right? So I can do a change of variable. So I'll just map x to M inverse x, right? Because M is an invertible matrix, and this is fine. So I'll get x, and I'm going to have Q0 transpose M inverse x equals 0, q1 transpose m inverse x equals 0, etc. So this is, I kind of draw like a little line between those two. So you see I have an m inverse x on all the equations inside this set, right? Now, this is basically a q0 transpose here, right, because it was a dot product. So if I pull the m in there, it actually needs to be an m inverse transpose applied to each of the q's. So that means that this is going to be equal to m inverse transpose q0, m inverse transpose q1, etc. Right? So I have to multiply by the inverse transpose of m for the dual version, right? And since saying inverse transpose becomes a little bit annoying, we'll just write it as m star for sort of the dual of m, right? So we'll just say it's m star. Okay? So that's the idea. So we want to basically, pull a matrix from one side to the other, so we just have to apply this, funny little operation to m, right, when we do that. So this is a thing that you kind of run into fairly frequently, right? Like if you ever do computer graphics, and you have like maybe a surface normal, and you want to transform it by some camera matrix in order to put it into like the view coordinate system, you pretty quickly figure out that actually like surface normals, because they're actually planes, so they're basically like a dot product vector, they're a dual vector, they transform by the inverse transpose of your camera matrices, not by your camera matrix directly, right? So it's a little bit of a funny thing that you have to be aware of, when you're working with either of these two representations. So it's important to keep in mind, whether we're working with points in this primal sense or points in the dual sense, or in physics, whether you're working with contravariant vectors or covariant vectors. So in tensor notation, you usually see this distinction between up and lower indices. It's the same thing that's going on here, right? Okay. So hopefully we won't have to mess with this too much further, right? But it's just important to keep in mind that there is a difference here, right? Okay. A few more transformations now. So now that I've said how these transformations actually work in projective geometry, I'm just going to go through and give you a couple of more examples of transformations. And then we'll probably move on to orientation. Yeah. So, okay. So those are translations. They're pretty easy. Another pretty easy transformation is scaling, right? So a scaling transformation is basically something which stretches the axes independently. So if you imagine if I have like a little like sphere here, and I apply some scaling independent along each axis, you can maybe create some ellipse, right? Like maybe squishes this length here and stretches out this axis. And scaling transformations in 3D can be written as basically the same as we, in the same sort of notation as we used here for translations, we can write out a scaling transformation. This is basically just a diagonal matrix, right, where we can just multiply each component independently. Pretty easy. And if you combine scalings and transformations, you get these things called homotheties, right, or homothetic transformations. Which are basically just scaling plus translation. It's pretty easy, right? I mean, you can just imagine that you just take this column and you just put it there, right? And one interesting point to note here is that translations are closed, so any number of translations will always get you back to a translation, and they're also invertible, so they form a group. Same thing for scalings, right? So they're also closed under scalings, providing these SXs are all like not equal to 0. And then if you combine them together, they actually remain closed and form another set of invertible transformations, right? So okay, so that's fine. So these are kind of the simpler ones. So now there are some more exotic transformations that are maybe a little more complicated, right? And probably one of the most fundamental ones is a reflection, right? And reflections are examples of what are called orthogonal transformations, right? So a reflection so here's kind of the idea, right? So imagine if I take, a plane and I have some figure, then a reflection in the plane just flips the figure around. So I would have to kind of I don't know if I drew that very well. I don't know. Whatever, it's a reflection, right? I mean, it's basically, or if you're dyslexic, right, you could say you have like a B, and then it becomes like maybe a backwards B. I don't know. If I do that too much, though, I'm just going to go crazy, right? Because I'll forget left and right. So I don't want to do it.
Shouldn't it reflect along the line?
Oh, yeah, this is reflecting along a different line, right? So just reflect along there. I don't know. Whatever. Okay, these are reflections. Right. Okay, so but here's the formal way to think about what a reflection really does, right? So a reflection, it's related again to this idea of parallel and perpendicular components. So if I want to do a reflection about some, axis n, right, of a vector x, then basically this is x minus 2 times n dot x divided by n dot n times n, right? Because basically this here, right, this is basically just, the, parallel component of x in n, right? That's all that this is, right? So if I imagine that I have, this is my axis n, this is my vector x, this is x parallel, this is x perpendicular, this is negative x parallel, this is Rn of x, right? So all I did was I started with x, I subtract off one copy of it, which is what that is, subtract off another one, now I'm down to here, to the reflected bit, all right? That's all that's going on. And we can simplify it a little bit if we assume that n was already orthogonal, in which case we could, just say, okay, well, the denominator here is 1, and then we could erase that. So if n is a unit, then we'll just say Rn of x is going to be x minus 2 n dot x times n. And that would be the reflection. Now in matrix form, we can just expand out the components of this whole thing, right? Which is pretty straightforward, a slightly tedious operation. But it's going to be 1 minus 2 times the, nx component squared, minus 2 nx and y, minus 2 nx and z, minus 2 nx and y, 1 minus 2 ny squared, minus 2 ny and z. I mean, you can just work this out, from the algebra there, right? So that's minus 2 nx and z, minus 2 ny and z, 1 minus 2 nz squared, 0, 0, 0, 1, 0, 0, 0. Okay, pretty straightforward. But that's a reflection matrix. Yeah?
If you're reflecting about n, how do you, get a picture there? How do you get something that doesn't, am I looking at that wrong? Or your diagram, if you're reflecting about n as a vertical axis, then shouldn't x be on the...
This is the reflected x. It's down here. So imagine x started up here, and I just reflected it down here, about n. Right?
What are you reflecting at about?
X-axis.
The n-axis, right? So there's this n-axis. You can imagine that there is a plane which is perpendicular to n. And so you can imagine that I'm just pushing it to the opposite side of that plane.
Okay.
Right? So you can think of n in one of two ways. You can think of it as either generating the axis, or you can think of it as generating a plane, which is perpendicular to the axis. Right? So that's the mental picture for reflections. Right? Now, reflections are interesting because the composition of multiple reflections is not necessarily a reflection, as it was in the case of these other things. But it's an instance of a more general class of transformations called an orthogonal transformation. So orthogonal transformations are basically the product of reflections. All right, so if you just keep reflecting over and over again, like you just pick another plane, you reflect, pick another plane, reflect, pick another plane, reflect, just keep doing that. What you'll end up with here is some crazy matrix. It won't be a reflection, right? But it will have an important property, which is that it's orthogonal. So if I take some matrix here, R, right, for that whole thing, I'll just say I have 0, 1, 0, right? Then this has the property that if I take R and multiply it by its transpose, then it's always equal to the identity matrix. Right. Another important property of orthogonal transformations is that they preserve lengths. So if I take the dot product of any two vectors and I apply an orthogonal transformation independently to each component, then the resulting orthogonal transformation, or the resulting dot product of their transformed images will be the same. So these are general orthogonal transformations. Now one key distinction is that these orthogonal transformations don't necessarily preserve orientation or handedness. So if you reflect something enough times, it might be, like if you reflect, in 3D, right? Imagine, you have like a mirror in front of you. Like the text is always reversed in the mirror, so it's flipped. The orientation is reversed. So if you have only orthogonal transformations which preserve handedness, right? That is that they are the product of an even number of reflections, then that's called a rotation, right? So a special subset is we have rotations, which are the product of even number of reflections. All right, let me see how I'm doing. I think I may be kind of burning a little too much time here. Yeah, okay. Right. So that's reflections and rotations. And I should say one quick word about rotations in 2D. So in 2D, the way you can think about the angle of a rotation is if you imagine if you take the two lines that you reflect about, then the angle that those lines form is the angle of rotation. And in 3D, if you reflect by any pair of planes, right, then they will have a common axis. That axis, or that common line between the two planes that you're reflecting about is actually the axis of rotation in 3D, right? And then the angle formed by the intersection of those two planes is the angle of rotation, right? So in this way, that's how rotations come about, right? It's just by, only doing an even number of reflections. So it's true in 2D that every reflection or every rotation is basically, defined by rotating about a single point. In 3D, it's a little bit harder to show this, but it's true that every rotation is a rotation about a line, right? But in higher dimensions, this is not true, right? Like they're just weird. Like so in 4D, you can actually rotate about two lines independently of one another, right? But this does not happen in lower dimensions, and we don't need to worry about it for now. So, okay. And I'll say a little bit more about the last one, but I really, I'm kind of running low on time here. So, erase that. All right, so the last type of transformation I want to talk about are shears and affine transformations. And so we have shears. So here's basically what a shear does. If you have a block like this, you apply a shear to it along some axis, then it basically pushes the x-axis to the side, right? So it'll basically skew it into like a parallelogram, right? And the matrix for a shear generally looks something like this. So you'll have something like SXY or SXZ. Right. So basically, it just looks sort of like an upper triangular matrix. And in fact, this actually can tell you something maybe about translations in projective geometry, because if you really think about what's going on there, which is that you basically have a kind of upper triangular matrix, a translation in projective space is actually a shear, right? So, algebraically, it behaves the same way, right? And it has the same formal properties as a shear. So what a shear does is it'll basically take like the y value and then push it up to x, or the x value and push it up to y, and so on, right? So these are shears, right? That's not much else to say about that, right? I mean, they're a pretty straightforward idea. And then finally, we have general affine transformations. So an affine transformation is something where you would have just a general matrix, M0, 0. Two, 0, M2, 1, 2, 2. Then you just have an arbitrary translation, T2, T1, T0, where this has to be invertible, and that's a translation. So an affine transformation can basically be any sort of arbitrary linear transformation, which is to say it can be a combination of a shear, an orthogonal transformation, scaling, and a translation. So you can just take any of them and combine them together. It turns out that actually shears, orthogonal transformations, and scalings are enough to generate all affine transformations. And this is actually related to a result in algebra called the Iwasawa decomposition of a matrix, which you don't have to worry about here. But suffice to say, these can generate that. And then a perspective transformation, or a projective transformation, just fills in these zeros at the bottom. And so these zeros, what they really allow you to do, right? So we'll just say that we still have our matrix M here. We have T. Then we'll have some, other stuff down here. So it's P0, P1, P2, and 1. And the effect of these projective transformations is that they allow you to move the line at infinity, or the plane at infinity, right? So you can then take that and move it to a different point. And this allows you to simulate things like a vanishing point in perspective geometry, or a vanishing line, or to model things like objects getting smaller in the distance as they would disappear. So you can have things like a frustum, or other types of visible structures. And yeah. Okay, so I think I'm out of time right now, and unfortunately I didn't get to orientation, which I really wanted to cover today because I'm going to be out of town next week. And there are a couple of questions on the homework that are basically asking you to calculate the relative orientation of different flats. So I may post an updated version of the homework that just doesn't have those in it because I just didn't get to that. So sorry about that. I'll probably get to them next time, and then also talk a little bit more about some algorithms, but I just went a little bit over time today. So, okay, we're going to stop here. I guess I'll see you all on the Monday after next Monday, or Tuesday after next Tuesday, right?
Are there any readings that you can be doing? Or I noticed there's linear lines. Is there a section of that? Or is that just a general reference?
Yeah, you can just read through that. I mean, I haven't actually given out prescribed readings yet.